Hello and welcome to our webinar today. The topic will be, what is good image quality? I think a question that many of us have already asked ourselves. It will be an exploration on the requirements between human eye and machine vision driven designs from raw to color processed image. Our speaker today will be Martin Müller. I will be your host today. My name is Frederik Schönebeck. I'm the Director of Product and Technology at Framos, and it's my pleasure to introduce to you today's speaker, Martin Müller. Martin Müller has more than 5 years of experience in the machine vision domain, and he is currently active to explore requirements together with customers for their various imaging projects in his role as a field application engineer for Framos. He supports customers in selecting the right off-the-shelf components, but also through their custom design journeys. Today, Martin will speak about image quality, and he will leverage all the experience he's gained in the years before. The agenda is structured in essentially 3 parts. We will start with a bit of a exploration of visual perception and what it means for the human eye and for machines. We will pivot over to image quality from raw images over to color processed images. And last but not least, Martin has prepared a bit of a benchmark where he compares leading smartphones with industrial camera modules. And to conclude the presentation, we will have a question answer session at the end. Before I now hand over to Martin, let me give you one more comment regarding questions. So if at any point during the presentation questions arise, you can use the built-in question feature of our tool. You will see at the top right corner a little question mark button. Please click this and type your questions there. We will get back to questions at the end of the presentation. With that said, Martin, the stage is yours.
Yes, hello. Also, warm welcome from my side to the European audience. Let's just start right away with the first chapter, the perception. In this chapter, we will talk about image quality requirements and the difference in requirements for human eyes and machines. And also there's one question that's like chasing me for a long time, or was actually chasing me for a long time. And this is like, why do budget smartphones or smartphones at all, or consumer electronics at all, outshine industrial vision systems? So why do they actually produce so good images, and why is it so hard to get to this quality using industrial grade equipment? So let me just start with a very nice example from my private life. So as you can see here, there are 2 images from a capture I did in one of the beautiful vacation places, Calaratiada, Mallorca. And so in my family, we share like the same cloud space for where all the smartphones are putting the images to. And when I recently scrolled through that library, I recognized that there were some duplicates. And I was just wondering why that's the case. And these duplicates usually have like this, as you can see here on the bottom, this kind of artificial warm colored filter on it. And I just asked my wife, hey, what's going on? Why is that the case? And she just said, okay, I do this because I like it more. And I like to do this when like favoritizing my images to recognize them. So the first thing that I like to mention here is that image quality is subjective. So one person likes the more warm tones. I personally like more the natural, so on the left side, but that's fully okay. So this is like personal taste. In general, an image for the human eye looks good when it is sharp, bright, and it contains vibrant colors. Also, images should not contain visible noise or artifacts or even optical distortion. So optical distortion is usually introduced when using wide angle optics, and it will cause to bend straight lines. You want to have like rectified, corrected images, like seen here. You want to have the rooftops, for instance, to be complete straight. What is also important is that images finally need to look good on displays for consumer grade devices. And also images need to look good on printers when you went to the printing store and print pictures from your family and so on. So, and this brings us to the topic of color space. Usually images for humans, they need to be have place in the sRGB color space, meaning that we will need to apply some gamma function to the colors and to the brightness so that the images look good to the human eye. That usually implies leaving the linear image color space. For machines, this is a bit different. So we have various applications starting from drone inspection tasks or even AI-based detection tasks. We have like navigation systems for mobile robots or even surveillance applications where low light is very crucial. So generally speaking, for embedded systems at all, the image needs to be good enough. It needs to be good enough for the machine to extract the relevant features from the image. And that usually means it's just tailored to meet the cost and shape of the system. So you don't want to over-engineer something because that finally takes, it costs money, which may be unnecessary. So, and also one very important thing is that usually the sensitivity is prioritized over the color accuracy. This is a major difference between consumer and industrial grade vision systems. So usually embedded systems are trimmed for color, for sensitivity. So they want to have a good response even in low light situations. Also usually images, they are applied in the linear space, so no gamma is applied. So let's consider the image quality and what it actually means and what it takes and what it consists of. As you can see here in this triangle, the image quality can be split into three parts, starting here from the image sensor and optics. So this is what I called the fundament, so the raw image. The image sensor plus the optics, they build the foundation in every vision system, regardless of if it's an embedded or consumer device grade system. And the raw image usually looks like a monochrome image. And you see here one of my favorite guitars, the beauty Les Paul Standard 60s. I like it very much. I took this capture with my smartphone in the RAW format. And just to show you here, when applying some magnification to this pickguard here from the pickup, you see here there is some kind of dotted pattern visible, which is the Bayer pattern. To finally process such a gray-looking image into the final color image, you need to apply some image signal processing to transform this image into the target color space, apply some corrections and optional enhancements. Especially enhancements, they are very important for consumer-grade devices because it will make the image look satisfying to the human eye. So the most important thing to start, so we won't be able to cover all the aspects of raw image quality, but let's consider just the most important in my opinion. So this is at first the quantum efficiency. So the image sensor, it acts like a transformer from photons to electrons as shown here on the left side. But not every photon will become finally an electron. And this is a ratio. So the amount of incoming light photons and the output of the image sensor in electrons. So generated charges. This is a ratio which is called quantum efficiency. And you usually want to be that quantum efficiency as high as possible because you will make your life easier when post-processing the image and making it look good finally. Usually the quantum efficiency is dependent on the wavelength. So for higher wavelengths, it will decrease, which is a natural phenomena of silicon. As a rule of thumb, a bigger pixel in the sensor will cause good quantum efficiency, better signal-to-noise ratio, and dynamic range. But there is a trade-off because big pixels and big resolution usually mean big image sensor, as shown here on this image. And big image sensor means big cost because the sensor price is per square meters of silicon. So the quantum efficiency shown on the previous slide was just for monochrome pixel phototone detection. But on color image sensors, we have on top of the photodiode, we have a microfilter called color filter array. And its purpose is for the post-processing algorithms to interpolate the Bayer pattern, so in red, blue, and green, to the final processed colors. That means we have to apply this kind of triple band pass, or it will act as a kind of triple band pass on the image sensor surface here. And for color, for most accurate color reproduction, usually used in consumer electronics devices such as smartphones or digital cameras, the focus is on good color separation. And the color separation can be read out here in this diagram. Especially the blue and the red color, they need to have a very good color separation, because here on this spectrum, you see the blue and the red, they have nothing in common. So you don't want to have red light portions in your blue frequencies. And there are actually two spots here that should have very good color separation. So for a typical embedded vision sensor, this is a bit different. So as being said at the beginning, color reproduction is not of most importance. It's more like the sensitivity. And you see here on this response that you have some color pollution between the green and the red, between the red and the blue, at least a bit, but this comes at a higher sensitivity, a higher overall sensitivity, and especially a higher sensitivity here on the near infrared. And this is usually something you want to have avoided in consumer grade devices, because it will cause color pollution in case you do not use an IR cut filter, and it will like become this purple tint in the image. For security applications, for instance, this is not a problem. Color pollution is not of that big problem, because at night, you know, gray cats look gray. To increase low light sensitivity, even on high resolution and small pixels, smartphones do a nice trick. So modern smartphones, the image sensor is contained of quad Bayer patterns. So this is a difference to what I've explained. We have here, like, instead of a single red, green, and blue microfilter, we have like clusters of each force adjacent to each other. And with digital remosaicing, which is a kind of complex algorithm which needs a certain calibration, the smartphone can compute a real native 48 megapixel image, so at full sensor resolution, which is nice during daylight situations when you have sufficient light, when you don't have problems with noise and quantum efficiency at all. You can get very nice, sharp, detailed images. But when it comes to night scenes, then the smartphones do a trick. They do like a binning feature, which will combine 4 adjacent clusters or one cluster into one filter. So it combines always groups of 4 pixels to 1, which means the resolution will drop from 48 to 12 megapixels. But at the same time, the signal at the pixel becomes 4 times higher. So that means you have better light sensitivity and you have less noise. And finally, usually smartphones do a back conversion and upscaling back to the native resolution, so that you won't even notice this on the final image, because 12 megapixels is still a high resolution. By the way, this capture here was done in Hamburg during a visit of the Miniatur Wunderland. I can really recommend doing that. Staying at low light performance, there's also one very important topic I'd like to highlight, and this is the lens, or more strictly speaking, the aperture or the f-stops of the lens. So the aperture actually is like a diameter which only lets through portions of the light to the image sensor. And this has physical, optophysical reasons. I don't want to highlight this right now, but you can imagine this aperture is required to get the image sharp on the image sensor. And it will, on the other hand, act like a barrier for the photons. So the higher the f number, the more shallow this barrier will become, the less photons will reach the image sensor. For instance, let me put just this practical example. We have here an f0.2 aperture versus an f1.2 aperture. Higher number means smaller image smaller way to pass for light to pass the image sensor. So higher f number will produce a darker image. And the difference is really huge. So between f 2.0 and f 1.2, which is only difference of 0.8, the amount of light which is coming through the 1.2 is 2.7 times higher. And you see it here on a practical capture what that difference really makes of. So also the optics is like a huge topic. I'm not able to cover all these in detail today, but let me just try to summarize the main chapters of optics that play a major role for selecting and for creating optics. So we have MTF, so sharpness, resolving power. We have uniformity, so like how does the sharpness behave in the image center versus the image corners? And also the relative illumination, which is a natural phenomena of optics that usually at the corners, optics become like a bit darker. Then we have flare and stray light effects. So when sun or any like intensive light sources are shining into the optics, you will see some artifacts called flares or glares. And also the distortion can play a major role, especially when having wide open angle optics, because it will compress the image resolution at the corners. For embedded vision, we usually select off-the-shelf optics, which is usually an M12 up to M8 up to M12 optics. And this is because of the quantities in the field. So for embedded vision, you can say it's very different, but roughly as a rule of thumb, hundreds to 10,000s of units or multiple of 10,000 units in the field usually. So that just justifies a certain amount of development efforts. And yeah, we usually select what is available, do optional customizations, and then topics like alignment, so focusing, multi-ROY or active alignment play also a role here. So usually it's always a trade-off in embedded vision. It's a trade-off between cost and the optical performance. For smartphones or consumer device units, this is a bit different. So we have usually millions or multiple of millions of units in the field. And this justifies a very, very high amount of NRE, so development efforts for this kind of category, for this kind of market. And usually smartphones or consumer electronics, they have more like a product character where a lot of effort is put into that it feels good, that it generates good image quality at all. And this is because the optical design is tailored, special made for a single unit. And you see even here that it's a very, on the iPhone, we have like a triple optics, which has a very, very small height. It's like very special made and utilized to get the most power out of the system. So let us have a look on a typical image signal processing pipeline from raw to final image. So at a very high level. So mainly when it comes to objective image reproduction, applying pipelines, we are speaking about corrections. And this is what happens in all systems, in consumer electronics and also in industrial vision components. Starting here from defective pixel corrections from the Bayer image and black level, we apply some debayering algorithms and finally color corrections to compensate what I've shown before, these color filter responses like pollution of red and blue and so on. This is all subject to debayering and color correction. But still, when you apply the debayering, the image usually looks a bit greenish. So this is not what you actually want. You want to have a natural looking image, a white looking image. And this is where the white balance comes into place. This is also very important to be applied to make the image look natural and more correspondent to the source. And then we have what I call the extra mile enhancements, which are typically within the nonlinear mathematical operations. So in smartphones, usually we are doing gamma correction. So to have like a better distribution of brightness values optimized for human eye. We have noise reduction, image sharpening, and also features like tone mapping, HDR, and also AI features we don't really know, but it's just all for enhancements. And you see here the difference is quite huge when you compare like from here, from the very right to this step, the last step from the white balance. So this is actually what consumer electronics do. So they are going this extra mile, while industrial systems usually they stop here. So the pipeline is just not so long, but it also doesn't take so much computing power because it's not required in many cases. Not saying this is always the truth, but in many cases it's sufficient to stop here. So how to do that actually? So to get from a raw to a final color image, you need to apply some parameters. You need to tell the debayering and the color correction how to do it, how to do the white balancing, and so on. And these parameters, they are the outcome of ISP tuning. This is usually happening with you need some measurement equipment and know-how. You need access to the tool chain of the ISP, of the vendor, to get out the necessary parameters. So this is the process we usually do at Framers for our camera modules to produce images that are similar like white balanced images. And you can see here some examples. So this is the output, so the color matrix, color correction matrix that was found in the raw image of the iPhone. And here we have the color correction that is applied within the NVIDIA ISP. So now let's try to visualize what it actually means and compare the iPhone versus an industrial embedded vision graded device such as the FSM Go. And just as a disclaimer here, it wasn't so straightforward to do this comparison because you're always kind of comparing apples with bananas. So these systems are so different, and you need to do some tricks to actually receive a baseline for this comparison. So let's start here with the iPhone 15 capture. I chose a low light situation. Why? Because it's usually a tough situation for image sensors. So low light means usually tendency for higher gain, more noise. So it's all in all much more difficult for the image sensor to generate a good looking image. So let's have a look on these metrics here. So on the iPhone 15, you have an image sensor 1/1.56 inch, 48 megapixels native resolution, and in bint mode 12 megapixels at 2 micrometer pixel size. The iPhone uses an f/1.6, so a quite wide opened aperture. And in this specific scene, the iPhone chose to use an exposure time of 1/15 seconds, corresponding to 66.7 milliseconds. And it chose a gain of ISO 2000, which can be roughly translated into 26 dB of image sensor gain. So this actually was a raw capture. Why did I choose a raw capture? Because I don't want the iPhone to do too much of post or pre-processing at all. I just want to have a baseline. And I took the raw image together with these parameters, like for color correction and white balance. And then you can use some tools on your PC, like raw therapy or Adobe Lightroom could also be possible to transform the mosaic image into a color image. And this is what I did here. And this is the result. On the other hand, we have the FSM Go's IMX678, which is, I guess, a good candidate for a comparison because it uses also a 2 micrometer pixel, and it has a similar sensor size, so it's not so much different. And also the resolution is in the ballpark. So we have here 12 megapixels versus 8 megapixels. I set the exposure time to the exactly same value as the iPhone chose, so 1/15 seconds, and I applied a gain of 24 dB, which is also similar to the iPhone. So just noting that the FSM Go 678 uses an f/2.7, and you already learned what that means. So I was kind of surprised that our FSM Go imaging module produced almost the same, so a very, very similar image, considering the sharpness, considering the brightness, and also the noise, with an f2.7 aperture compared to the iPhone 1.6. And this Yeah, this is due to the sensitivity of the image sensor used here. The 678 is a Star-2 sensor trimmed for low light applications. So on the other hand, what we else do see here, we see here some flares caused by the optics. Yes, and also some optical distortion because there was no optical distortion correction applied. So now it becomes really interesting and amazing. So let's compare the iPhone 15 left versus the iPhone 15 right. Left is the image I've just shown, and right is the image which comes out of the camera application with all possible features enabled. And the difference is really, really amazing. So for instance, dynamic range. We see here in this bright spot, it's not even possible at all to detect details in the bright scene. Here on the right, perfectly dynamic range. It's an HDR image actually. It's perfectly sharp. We have here like textures which are which they even seem like artificially pronounced and optimized. So there's a lot of things going on. And if you go to the Apple side and check the camera specification, you see these proprietary algorithms like deep fusion, smart HDR5, night mode, true tone flash. We don't even know what these things are doing. I would consider these algorithms to be sort of AI processing. So as a summary and takeaway for you, image quality is different for human eye and machines in terms of requirements. Also, both devices need to have good raw image, good quantum efficiency, SNR, and dynamic range. Usually bigger pixels have an advantage here. On consumer device graded devices like the iPhone 15, it let outshine the FSM Go image quality visually completely. But however, when considering the raw image, it has a very similar image, meaning that this is because of the enhancements and algorithms going in the background the iPhone is applying. And this is because consumer electronics usually have more space for high development costs because of the high amount of units and also the user expectation. It needs to be a nice product and a nice look and feel character. It needs to have a nice look and feel character. So that brings me to the end of my presentation. And now it's time for your questions and let's get into a discussion.
Thank you, Martin. Great presentation. Yes, it did trigger a couple of questions. Let's just start already with the first one. Binning, you mentioned binning is happening also in phones. For CMOS image sensors, is it right to assume that the binning actually happens already in the charge domain, like for CCDs, or does it only happen later?
Usually, so it depends on the image sensor used. When speaking about Sony, in this case, this usually happens in the charge domain. So charge domain here means more on the analog side, that you combine really the power of 4 photodiodes to 1, ensuring to have a more surface to collect the light. So you have like 4 times higher sensitivity. Yeah.
Okay, thanks. Then another question related to the comparison between the iPhone and the Framos camera module. You were able to acquire a raw image from the iPhone and then also applied a manual camera pipeline flow subsequently. How did you do that? So how did you acquire the raw capture, and which kind of workflow did you manually apply later on?
Yeah, I was actually surprised that this was actually possible with the iPhone, because I thought usually that this is not opened from Apple, but it seems like this was changed recently. So for the iPhone 15, or starting from the iPhone 15 Pro, so I didn't use the Pro, but the Pro serves a native RAW support from the camera application, so the usual camera application, and you can get this kind of image directly without any additional software. In my case, it was an iPhone 15, and it was not possible doing that, but it was still possible using a third-party app, which is called Pro RAW. I think, oh no, it wasn't Pro, it was Apple RAW also. So in the App Store, you find an app for this. And this will allow you to still do raw captures. So, and then with this raw capture, it will come in a format from Adobe. It's called DNG. So it's like .dng, digital negative. This is a standardized format from Adobe, which contains all the information like color correction, white balance, black level, and also geometrical distortion correction tables, so that you can really do the complete workflow with a third-party program on your computer. Such a computer program could be Adobe Lightroom. So this is, I guess, the most known. But there are also free tools like Raw Therapy available.
Okay. Thanks. I think that gives a good sort of picture in which direction you were doing this. There's actually a few more questions, but I'm afraid we can only tackle one last one. For all the ones who still have open questions, we'll reach out to you offline and get in contact with you one by one. One question regarding color correction matrices. How many do you actually need, or how many did you use for the 678? Was this just one, or was this multiple when you did the calibration for the 678, IMX 678?
So the calibration for the 678, this takes place in our imaging lab at Framos with some, so it's at the end, it's a single color correction matrix, a 3x3 matrix. That's the final result. But to get to this result, you need to apply, or we at Framos, we apply several different light sources with different light color temperatures. And yeah, there's like a way how to do that, which is not so, I think, not officially available. So you need to have some internal know-how how to do that, and even support to the ISP toolchain. But the general approach is here: take different light sources, take the same color pattern. You iteratively went through this process until you have a good-looking, neutral-looking color checker pattern. And then the output would be a 3x3 color correction matrix.
Okay, thanks a lot. So
you're welcome.
I will close the presentation here. Thank you very much, Martin, for this very nice presentation. Thanks for the audience for so many questions. As I said, we'll follow up with all of you to get those questions answered. And it was my pleasure to host this meeting. Have a nice Christmas. Have a nice end of the year, and see you again next week. Next year. Sorry. Bye-bye.
Take care. Goodbye.